is generation of narrowband bright single-mode squeeze light through Feedforward by Saesun Kim, also from the University of Oklahoma.
Hi, my name is Saesun Kim from University of Oklahoma, Quantum Optics group by Alberto Marino. And I'm going to talk about how we can generate the atomic resonance squeeze light using the Feedforward technique. And this work is supported by the Air Force Office of Scientific Research. So squeeze theta light is a quantum state of light which has a reduced noise property. And due to this property, people have been enhanced the sensitivity of atomic sensors, such as optical interferometer. This idea was first proposed by Cave in 1981, and now they are trying to enhance the sensitivity of the gravitational measurement of LIGO. And also this enhancement has been applied to the different systems, such as plasma sensor and quantum imaging. So people are also interested to enhance the sensitivity of atomic sensor because atom can be well controlled and sometimes it gives extreme sensitivity. So if we can enhance the sensitivity, then that would be really good. So in order to do that, we need to have an efficient interaction between atom and light. So then we have to generate the resonance squeeze light. So once we can generate the resonance squeeze light, then we can either propose and achieve to enhance the sensitivity of atomic interferometer, atomic magnetometer, and spectroscopy. So commonly, people generate the squeeze light using the crystal and process using the optical parametric oscillator. And usually this process inside the crystal generates the broadband spectrum. But by fabricating the crystal and then putting into the cavity with the locking, people have been generating the narrowband spectrum. However, still the challenge is when they try to generate the resonant case, they have to pump with the UV frequency because they have frequency doubling. So parametric conversion. So then UV frequency have a lot of losses inside the crystal, so it often becomes a challenge. But they managed to, despite the challenge, people managed to generate the rubidium and cesium resonance squeeze light using the crystal. So alternatively, if we can generate the squeeze state light with the atom, then this is already generated with the narrowband, and it's already near the resonance, so it will be much easier and more natural way to generate it. So common way, two different ways to generate the squeeze light. One is the polarization self-rotation, and one is the four emitting process. However, when they try to get it to on resonance, because now strong interaction between the resonant transition, so then it get all absorpted, and it's kind of challenge to generate it. So polarization self-rotation, they generate on resonance with the rubidium and rubidium D1 and D2 line in the single mode. For the four emitting process, this is slightly different because they generate a two-mode squeeze light with the large degree of squeezing. So last year, we generated about 5.4 dB on resonant, and in our lab, we can generate about 9 dB of squeezing near resonant, and other people have been generating about D2 and cesium D1 line. So you can see that four mixing process can generate the two-mode squeeze light, and they have interesting properties such as entanglement. However, in particular for the sensing application, people show that single-mode squeezing is better than two-mode squeeze light. So then in my talk, I want to talk about how we can generate the single-mode squeeze light from the two-mode, by the converting two-mode squeeze light using the Feedforward technique. So then we can use the large degree of squeezing and we can make it on resonance. So the Feedforward technique is shown here. So first, we have a two-mode squeeze light. We call it probe and conjugate. They have a quantum correlation with each other. And because of this correlation, each beam, when you look at it, they have a large fluctuation. So we can measure the large fluctuation of the conjugate beam and use that information to reduce and correct the noise of the fluctuation of the probe. Then after the feedforward, then we can get a reduced reduced fluctuation of the probe. And because they are quantumly correlated to each other, this will give us a single mode squeezing, and we can get it below the shot noise. So we can calculate what we are expecting. So all the S's and noise spectrum normalize to their shot noise. So you can see that S here is noise after the feedforward, and S is a single beam noise of the probe, and then S minus is an intensity different noise, so noise from the two-mode squeeze state. So you can see the first term is just simply the coupling of the feedforward losses to the vacuum couple as a vacuum noise, and the second term is a noise reduction from the feedforward. So in ideal case, when you have a perfect transmission of the feedforward and a perfect detector efficiency, we are expecting that before the feedforward and after feedforward, the noise should be, absolute noise should be same. So we can perfectly transfer all the noise, and we should get the same noise before and after. However, because we are detecting half of the noise, half of the beam, then we are normalizing to the half of the light. So that's why in ideal case we pick up the factor of the 2, which corresponding to the 3 dB losses. So then when we service a 9 dB of squeezing, then we will get a 6 dB of squeezing in the ideal case. So for the generating the 2 more squeeze state, we're using the Fourier mixing process. Fourier mixing process is a nonlinear process involving the 4 photons. First, we have a 2 photon get absorbed, and when it absorbed, simultaneously probe and conjugate are generated at the same time. This is experimental setup. So you can see the probe and conjugate generate simultaneously into the photon level. So when you measure intensity fluctuation, they are correlated. So when you look at the noise, then you will see that it's below the sound noise. So our lab can generate about 9 dB of squeezing of resonant case. So when you look at it, when you measure the conjugate and feed forward to the probe, then our probe is still off resonance to transition. So we want to make it on resonance single mode squeeze the light, so we can try to tune the 1 photon detuning, which is 1 photon detuning is the detuning from the ground state to exact state. So we try to tune the 1 photon detuning so that we can try to make it on resonance. However, when you try to do it because of the strong absorption, we cannot really get any squeeze light out. So instead of trying to tune it on resonance, we're going to take advantage that rubidium has a different isotope, which is rubidium 87. So we can try to tune 1 photon detuning a little further so that we can tune the probe to be resonance F2 to F2 transition of the rubidium 87. And this more detail is in this paper. So now we can measure the conjugate and feed forward to the probe, and we can generate the resonance squeeze state line. So this is experimental setup. Here we have our Fourier mixing process, and before we put the probe into the Fourier mixing process, we measure a small part of the probe into the saturation absorption spectroscopy, so we can measure our probe is on resonance or off resonance. And after that, we have a feed-forward setup. And then feed-forward setup, you can see that there is a electronic delay because detector and UM will introduce some of the delay. So in order to compensate the delay, we introduce the optical path. And we optimize about 20 meter, which corresponding to about 65 nanoseconds from the electronic delay. So then when you do it, we have two different cases, off-resonant single mode squeezing and on-resonant single mode squeezing. When you look at the off-resonant case first, so we measure sound noise, and we measure intensity different noise, and we measure single beam noise. And using the theoretical calculation, we can get the prediction. So you can see we service the 7.7 dB of squeezing, and we reduce the 3.6 dB of squeezing. Before I mentioned that in ideal case we will get a 3 dB reduction, but here we got like 4 dB of reduction. This is because of the losses from the feed forward and then not perfect detector. So when we measure the feed forward, and we got about showing in here, and you can see the feed forward trace is going up as the analytical frequency increases. This is because we are limited by the bandwidth of the detector, which is a 4 MHz. So we get about 2.9 dB of squeezing from the off-resonant case. For the on-resonant case, from the 5.8 dB of squeezing, we got about 2 dB of squeezing on resonance F2 to F2 transition of the rubidium 7. So here, I show that we generate a resonant single mode squeeze light, off-resonant single mode squeeze light with a 2 dB and 2.9 dB of squeezing. And this is mainly limited by the transmission, the losses from the feed forward. And we believe that this can be improved by bypassing the UM. So this group have shown that we can bypass by using the high reflecting mirror, and using that we are getting prediction of 2.8 on resonant and 4.3 off resonance. So I want to acknowledge, I have time, so I will acknowledge that this is my advisor, Alberto Marino, and this is postdoc Ashok Kumar, and this is all our group. And thank you for your attention. When I measure by the detector?
Yeah, you show the noise reduction. You're measuring some noise power spectrum. So are you showing the total noise or it's a noise power spectrum? If you're showing the total noise, then my question is, what's your integrated bandwidth?
So are you talking about the, if I understand correctly, are you talking about like resolution bandwidth or video bandwidth or detector bandwidth?
Okay, so what's your resolution bandwidth?
So if I remember correctly, it's 30 kilohertz, and then the video bandwidth is like 100 megahertz.
100 hertz.
100 hertz, sorry, 100 hertz, sorry.
the bandwidth of your feedback is?
A feed forward, you mean?
Or feed forward?
I think it might be just mainly limited by the detector, which is 4 megahertz. But we believe that we can design the electronics to make it better. We're using a different detector setting to make it better. But we couldn't really make it better yet. So.